That work? Yeah, thank you.
Okay, so I'll talk about gamma simulations. So I'm a lead developer of the gamma helium model at APL. So what I'm going to talk about in these couple slides are CME simulations of coronal mass ejections in the steady state solar wind background for now. So again, the solar wind background is driven by the WSA coronal semi-empirical model, and the CME is represented as a sphere Mach or a tethered sphere Mach, which is described by the Gibson law CME model. And so I'd like to show just a couple examples on the right side. So this is the synthetic images of total brightness and polarized brightness in a couple of cases. So on the left, so we're looking at the case of a wide CME interacting with the solar wind background, and especially I would like to take your attention to the distortion of the CME front that happens due to interaction of a CME with the background stream interaction region. So having both synthetic images and simulations really help us to understand what we're seeing in these images. So another case on the right side, this is the case when the CME overtakes with the stream interaction region, and it creates higher plasma compression on the flank of the CME. So we see this increase of brightness on the side of the CME due to this kind of interaction. So we are running different simulations with different solar wind backgrounds and different CME configurations, and then looking at the images and having ground truth simulation data, we can try to understand what happens, what kind of interactions happen in these images. And now I would like to talk about the high resolution gamma ray simulations. As we all anticipate, PUNCH will have unprecedented data, and we will need unprecedented modeling tools to complement this data. And Gamma model has a high resolving power. It's not just the high resolution, but also the ability to resolve structures within a limited number of computational cells. And this is the key to resolve the mesoscale structures that can form due to interaction with CME with the background solar wind. And these high resolution simulations really offer us opportunity to understand the details of CME solar wind interaction at global scales and at mesoscales that PUNCH will observe. And just a few examples here on the left. So these are the high resolution simulation that we have done recently, and we see that the CME shock, as it overtakes with the stream interaction region, it can really develop a lot of different irregularities and corrugations at the front. We also see substructures in the CME sheath at mesoscales. The whole CME structures get distorted quite a bit in these high resolution simulations. And also the stream interaction regions, they're not just smooth large scale structures, they have sort of the micro structures within them in these high resolution simulations. And so PUNCH will see all these mesoscale structures development in the inner heliosphere, and I think this is the great synergy between the high resolution gamma modeling and the future PUNCH data. And I'll turn to the next speaker.
Thank you. The next speaker is Cooper Downs.
Yes. Fantastic. Great. So yes, happy to be here. And I'm here to basically represent predictive science and the type of coronal modeling and heliospheric modeling that we can do. And I prepared this stuff kind of with the theme of not only what is the cutting edge science that we're doing, but also what sort of tools and data products that we have that might be of interest to the sort of broader community of PUNCH users as well. And I also want to say that I have a poster out there. There's QR codes in here, but please feel free to come find me at the poster session if you have questions about anything I show here. Right, so at Predictive Science, we're the developers of a code called MASS, and it's we call it a thermodynamic MHD model for the corona, but MASS can also be coupled to the inner heliosphere, so basically covering from 1 RS to 1 AU. As was pointed out in earlier talks, a key input to this type of modeling is the magnetic boundary conditions. For a thermodynamic MHD coronal model, you might also have coronal heating, and then that can generate a lot of things that might be of interest if you're interested in studying what is the context of a particular observation. What was the corona looking like at the time? You can do forward modeling, you can look at the magnetic field, you can even do solar wind or in situ comparisons. One of the three things that I'll go over is a resource of basically models that we've already pre-computed, that we compute regularly, at least once every Carrington rotation. And we've built, for a long time, we've operated a website called MHD Web, where a user can log on and then go navigate model results for coronal and heliospheric models. We have several that we run for every Carrington rotation. And we're also revamping this website, which is why there's two QR codes. This is kind of in beta right now, but a new version of this website that will allow more interactivity and different sort of more heterogeneous different types of simulations, coronal mass ejection simulations, time-dependent simulations, things like that. And of course, one of the themes is for multiple spacecraft analysis. So spacecraft connectivity mapping, data comparisons. And I had our software engineer add both NIFI and WIFI to our MHD web modeling site. Another tool that I think is really useful for the community is something we've delivered to the CCMC, NASA CCMC, which basically took all the complexity that it takes to model a CME from the source region erupting out into the lower corona, the middle corona, out into the 1AU, is basically encapsulate all that into a series of steps where anyone can go on and build a coronal mass ejection simulation. People who outside of predictive science have already used this for their science, for writing papers and things like that. But basically, this is a tool. If you're interested in a CME, you can go try to build it and then get the data from the CCMC. And last but not least is sort of the new frontier, and thank you, Evangelia, for introducing this so nicely, is introducing time evolution into this sort of coronal modeling. And mass is sort of unique because we go from 1 RS all the way to 1 AU with this sort of coupling. So we can couple our model directly to the flux emergence and flux evolution of a surface flux transport model at the base of the corona and drive a lot of different dynamics. So as Nikki was saying yesterday, with PUNCH, you really want to know what is the source region and evolution of all the stuff that we see. You can model all the various different coronal dynamics and then connect them all the way out into the heliosphere. So this might be like coronal mass ejections, streamer, pinch-off, blobs, things like that. And just I'll close with some fun movies that just sort of illustrate what this kind of simulation looks like. Thank you, Erica, for generating this cool Punch movie with the rotating trefoils. This simulation was 1 hour cadence, so it's going a little faster. But basically, you're seeing as Earth's view is sweeping across the magnetogram, we can generate all these different sort of forward model diagnostics, low corona, mid corona, sort of coronagraph type observations, and then connect them out into the heliosphere. And of course, as Evangelina pointed out, when you have a time-dependent simulation, this one also has coronal mass ejections as well, because we're energizing the corona in addition to our driving, where there's just a lot of really unique structures that comes out. The heliosphere is very dynamic. Of course, this is solar maximum, but still, that's an example. Thank you.
All right, so the next one is Chip Manchester. Okay, yours is easy to spot.
Okay, I'm going to be describing results of simulation producing mesoscale structure. This is done with the AWESOME model, the University of Michigan, with their very self-deprecating title for the model. And what I'm presenting this as mesoscale structure is definitely pointing out as one of the major science topics that will be addressed by PUNCH. And so we're looking at examples where the structures can form, particularly in very complex circumstances where coronal mass ejection is going out in solar maximum conditions, as shown here in September of 2014. In the left image, you're looking down from the pole onto the structure. You're actually seeing the streamer belts face on, looking downward. So the heliospheric current sheet is passing directly over the poles. On the right image is showing the full heliospheric image of the model going out to 1 AU. You can see the development of the fast and slow streams, the current sheet for this heliospheric separator. And the CME is going out right down at the center, right into the fast stream, impacting the slow stream. And so this is a super high resolution simulation of this type of event, showing how these type of mesoscale structures can form. And evolved through the solar wind. They're forming here at the cusp of the coronal mass ejection. Again, we're looking at a polar view, XY coordinates. The North Pole is looking down from the North Pole, showing the magnetic field strength, the BZ component, which is very geoeffective. Zooming in on a little box is where the reconnection is occurring, that's resulting in the formation of a magnetic flux rope at mesoscales. And then we track that out to 1 AU. And so this is showing that structure as it approaches 1 AU. Again, a little black box, and we're going to zoom in 2 times for factor of 2, then 10, and then finally 50, showing the adaptive mesh. And using the block adaptive mesh, we can actually find this to 1/16 of a solar radius all the way out to 1 AU with only about 250 million cells. But if this were a uniform grid, it would be about 10 billion cells. And so on the right is showing the full 3-dimensional magnetic structure of a pair of magnetic flux ropes that have formed as a result of the collision with the coronal mass ejection with the stream interaction region. Okay. So that's basically it. There's a lot more details in the poster, which is right over there, right through the doors. And in particular, it shows the density structure variation, which is also very highly structured on the scale of these flux ropes. So you actually should have an image of that. But again, it's in the poster. And so the variations in density range from about 20 to almost 100 particles per cubic centimeter in this cluster of magnetic flux ropes. So it is certain to have a strong signature on that scale in the Thomson scattered white light. The next thing we want to do is make a series of images of Thomson scattered white light on that scale of the punch imager, and again, track that type of feature out to 1 AU. So again, I definitely anticipate that our simulations will be able to reproduce the structure at the adaptive grid, and we'll have an observable component in punch.
All right, our next speaker is you, Bill. All right, so we next have Bill Matthews.
Pictures aren't.
Mhm.
Yeah, I'm Bill Matthews. I want to talk about the Usmanov code, which doesn't have we keep on asking Arkady to have a cool name, but he won't agree to one. So I want to applaud my colleagues for having time dependence. Angelina, I guess, talked about time dependence, and Anya talking about high spatial resolution. Our approach for the last 20 years or so that this model's been under development has been to try to get the basic physics correct. We don't do anything funny with ratios of specific heats. We don't let the electron heat conduction pull the protons out. We don't do all kinds of stuff that makes it easy to get a high-speed wind, but we have a code that does get a high-speed wind with pretty close to correct physics all the way down to the coronal base, whatever that is. We don't have a really good chromosphere in this code yet, but we're working on that too. But what we do have is we have turbulence transport modeling. So when we developed what's now called the reflection-driven model or the wave turbulence model back in the late 90s, we knew that it had to be coupled to a large-scale code to get things correctly. And it took more than 10 years to get all that working correctly. So now we have a global 3D code that incorporates turbulence modeling, and that's self-consistently coupled to the large-scale momentum transport and so forth. Now, the thing is, if you were Ford or BMW, you would not design a car, you would not design a Boeing airplane without turbulence modeling. It's not possible to simulate extremely high Reynolds number flows accurately without turbulence modeling. No computer can do that. People do a pretty good job of it. I think one reason is because the characteristics in the solar wind separate fast enough that information basically flows from the inner boundary without interacting. But if you want to get the fine scales, you have to get the sub-grid scale information accurately. So anyway, we use Reynolds average equations. We specify boundary conditions at the coronal base. And what new physics do you have by keeping track of the turbulence? Well, 2 things that I can think of is you can do field line random walk, which you can't do if you don't resolve all the way down to the sub-grid scales. And therefore, you can do SEP transport because you can get the diffusion coefficients. So I'm going to just push here. And so this is the Reynolds averaging scheme where you have resolved and unresolved with a statistical separation. There's a 2-way coupling between the two. If you turn off the turbulence and just do a dipole, you get very much 150 kilometer per second wind and 605 kilometers per second with it turned on. In terms of more detailed things, when we use the ADAPT model, and our higher resolution. This is what we get for speed, density, magnetic field, and in the right, the turbulence parameters. So the right-hand column has the parameters that you need to get scattering of SEPs. So we have that as part of our self-consistent solution, and I think we do a pretty good job. But I think some of the other codes are ahead of us in other ways. But I think if you need some grid scale modeled and turbulence to do some of the things that we would like to do. So thanks. That's all.
Right, next I think we have Tinnitin. You spot it. I think you've got the PDF, yeah, yes.
The end of that.
Got it.
Okay, hi. So I want to introduce some of the models that we have developed in Europe and we're using for reconstructing the whole domain from Sun to Earth. So I have 3 minutes to introduce 3 models to you. Oh, pressing on the, it doesn't,
Okay, hold on.
yeah. So I will start closer to the Sun with our coronal model that we have recently developed. Recently developed at KU Leuven. It's a global 3D MHD model. It's called Coconut, and it was developed for space weather purposes. So we support some advanced techniques. So it supports the fully implicit solver, for example, the unstructured grid, so our simulations are optimized and fast. So here we cover the domain from the solar surface until 0.1 AU. And on the right, you see the example of the solution in Coconut, so the density plot. And then we recently have generated the polarized brightness images with the FOMO code, which is also a forward modeling tool that was developed at KU Leuven. Let's then move further out in the heliosphere. So first I will start with euphoria, but Yasmin already introduced it quite well. So what I want to say here is that we start at 0.1 AU and we cover the domain until 2 AU, or if we need also further, we exclude the poles also in the domain. But one thing to pay attention is that here euphoria uses the uniform grid. So if you want really high resolution, then you have to have high resolution really everywhere in the domain. And also euphoria supports a bunch of CME models, the simple and also magnetized ones that you can launch from the inner boundary. And at the end, you get the global 3D, all 8 MHD quantities, which you can play with and then also create the synthetic images. But then I will also go to Icarus now, which is the alternative to euphoria. So it covers the same heliospheric domain as euphoria does, but it was developed with space weather purposes in mind. So it supports advanced techniques. And you can see in the middle that we support the radial grid stretching and AMR techniques to make our simulations really fast. So here I'm showing an example for tracing the CME, but we also have criteria for CIRs, and we're working for criteria for heliospheric current sheet so that we get these areas refined. But the big improvement and new development of Icarus that was published last week is that we also started driving in time dependently. So all the dynamics that Evangelia showed, we also started to see, but in the model, of course, because before we didn't have a way to actually see the observations of all these dynamics. And one last thing I want to say is that we have coupled Icarus, the time-dependent mode, to the Coconut time-dependent version as well. So we have also passed the whole CME structure time-dependently for all the way from the Sun to Earth to see its evolution. And then preparing for the PUNCH launch and this meeting, we have done the first attempt to generate the white light, synthetic white light image from Icarus, which you can see on the right top panel. And in the bottom, we combined the white light image that we can generate from Coconut and then go all the way with the synthetic white light image to Earth with Icarus. Thank you.
Okay, and there I'll let you. Whoop. Okay, we're going to move on to Christina K. Yes, okay. My button works. Cool.
I'm proud to say I have the least fancy model of anyone up here by a long margin, but that's somewhat by design. So Osprey is just a set of coupled modules, and they're all physics driven, but they're simple analytic things. We're not trying to do a full grid, do all the basic MHD physics in every grid cell. We're treating the CME as a sort of object that we can simulate forces on and push it around in the corona or further out and see how that influences its trajectory. So this is something that takes a minute to run on a laptop. It's not this big fancy simulation, but it's something you can do on your own and do ensemble simulation. So it's kind of designed for space weather, but having this very open sort of modular nature gives us a lot of freedom that you don't get with these sophisticated models. And so the basics of Osprey is there's 4CAT, which does the coronal deflection and rotation of CMEs close to the sun. And this is magnetic forces that are pushing things away from coronal holes towards the heliospheric current sheet. From there, around about 0.1 AU, would tend to move to the interplanetary version, which is Anteater. This is propagation that includes drag, CME expansion, and deformation and rotation. And we're, again, driving this all from basic physics equations as much as we can. And then the final component is FIDO, where it just makes you synthetic in situ profiles of the magnetic field and other plasma properties, density, velocity, all of those things. And so here's this nice block diagram showing you all the inputs and how the modules are differently connected. And one of the big things we can do with PUNCH is take some of these observations and use these to drive our inputs. And some of this is the standard things you would do with like a GCS fit, where you can get these coronal or the inputs of where the CME is located, the geometry of it, all that information that kind of goes in that purple block there. And there's different ways we can do it. I'm very curious to see how well we can do this using the polarized images, but we also can always just combine this with stereo or other off-axis information to try and get this triangulated images. It'd be interesting to see. I know Chris got some work trying to get the measures of the chirality of the CME. And if you're trying to simulate the magnetic profiles of CME, you need to know the handedness of the structure. So we may be able to pull information out that way. And then another big thing in the red here is a lot of this work is on how well we can see this background solar wind. And the solar wind is a major component of our model simulation. We're propagating a CME through it. So the better we know that background solar wind, the better we'll be able to simulate the CME's behavior in interplanetary space. And then some more kind of fun out there science improvements. Because this is so modular and so open, we can play with different components. We can tell it to have a certain radial profile or do something in the corona that you can't necessarily do with an MHD model by changing just the CME parameters. So if we have a well-observed CME, like this 2008 December case here, where we really know its radial profile and we know where it is and latitude and longitude out at distance, we can constrain that and tune our model to make sure that the results match what we see in the observations. And here's an example of things we might want to look at with a sunset is how different magnetic backgrounds affect the amount of deflection and rotation. So we tend to use just a PFSS background, but you can artificially scale that up by a factor of R or R squared so that it decays less with distance. And so then we can see how that affects how much deflection or rotation we do. So the better observations we have, the more we can tune sort of what we're looking for with our model, and we can maybe play around with some of these background parameters and try and get out information about the solar magnetic field or the solar wind and all of that interesting things. And so, yes, it's a very unsophisticated, but a lot of options and a lot of things you can play with.
Great, thanks.